Thank you. Hi, everyone. Today I'll be talking about the challenges and lessons learned from supporting multimodality on vLLM. First of all, just like overall agenda of this talk. This talk is about like a brief history of how we supported multimodal models on vLLMs, including the challenges we encountered, how we solved them, and the lessons we learned. And I'll wrap up with the future roadmaps and the future work in this workstream. And this talk is not about using diffusion models on vLLM. That's not on the roadmap yet. And we also won't be talking about multimodal outputs like image or audio generation. We'll be focusing on multimodal inputs and text outputs. Before I kick in, I want to introduce the multimodality workstream on vLLM. First of all, myself, I'm a software engineer on the ML platform team at Roblox. We are actively hiring. My manager is sitting right here, so feel free to talk to her right after. I'm also a committer on the vLLM project. I've been working on the project since February 2024. I, as many of you here, was a user of vLLM, so my first contribution to the project was like an online serving benchmark to compare different serving backends out there, TGI, TensorRT-LM, DSP-MI. And since April, I took over the multimodality support on vLLM to add support for all different kinds of like large multimodal models. I want to emphasize that this is a team effort, and here are a few key contributors in this workstream. First of all, Cyrus, he's a PhD student from Hong Kong. He and I kind of co-led this workstream, including all the roadmap items and the overall direction for multimodal models. We also have Zifeng and Xiaowei who have contributed to the workstream extensively. Xiaowei is from N-Scale. She actually made the first POC PR for vision language models I'll talk about in a bit. And last but not least, we have a few community members who have been contributing to the workstream, adding models, adding features, optimizing the vision language support, the vision language model support in the very recent 2 months. And finally, I'd like to thank my colleagues at Roblox for supporting me to work on vLLM part-time and giving me feedback on my overall design. Okay, so I'd like to give you like an overall overview of our large multimodal language models and why it makes sense to support them on vLLM. So recently, like as you might heard, like a lot of like image language models or audio language models, all they do is they leverage a language model backbone along with an encoder of a non-text modality, meaning you first kind of encode your image or audio clip or video clips with this vision encoder. Sometimes it's a clip encoder, sometimes a whisper encoder into the embedding space. And you project that to the same embedding space with your text embeddings. You concatenate or merge the two embeddings, and you send that through the language model to do the actual understanding or generation. And on the left, we have the lava architecture, leverage a clip vision encoder. On the right, we have the Q1 audio model that leverage a whisper encoder. And as you can see here, the most computation happens in the language backbone, not the vision encoder. And this is why it makes sense to support such models on vLLM, because as we all know, vLLM is a very space-efficient, fast engine for language model. So next, I'll talk about like the brief history of the support for multimodal models on vLLM. Back in March 2024, Xiaowei from N-Scale made the first PR for POC support for Lava 1.5, and now I'll briefly talk about why it's a POC support in a bit. And in April 2024 is where I came in. I met RFC for kind of refactoring the overall multimodality support, and this RFC has since become like a tracker for all the roadmaps, updates for this workstream. And in June 2024 is where we finished the first milestone where we refactor the user interface and support OpenAI Vision API compatible inference. Meaning you can deploy an open source vision language model and use the same OpenAI client to call this model. And July 2024 is where we generalized the groundwork for supporting vision language model to all modalities. This is really like a developer-facing change. All the developers, if they have like an audio language model, they can come in and plug in the audio plugin to the vLLM and support it on vLLM. So it's not tied to image in particular. And one more important thing here is that we support dynamic input shape that I'll talk about in a bit as well. And finally, like September 24 is where we kind of wrap up the third milestone, where we actually generalize to multi-image audio, video models, and we actually got day one release for Pixel, the first multimodal model from Mistral AI, and day one release for multimodal Llama 3.2. And finally, I encourage you to check out the roadmap. It's in the same issue as RFC, issue 4194 on the GitHub repo. Okay. I mentioned back in March, the kind of the first POC supports really POC. Why is that? So let's look at like what did it look like back then. This is how you initialize a Lava 1.5 back then. You first initialize the model, you format your input prompt, you load the pixel values, and you do the actual inference. There are a lot of overhead in this interface. First of all, there's some metadata that users will have no idea about. Some developers they don't have any idea like what they are actually. And you have to pre-format your image, I guess your input prompt with the additional input tokens. These are input tokens as placeholders for the actual input image embeddings. And this is not a Hugging Face format, so sometimes the user have no idea how to get this actual number. And lastly, the image data format, input format, is actually pixel values. A good analogy for this is that pixel values to images are like prompt token IDs to your text prompt. So the user will have to understand how to actually process your JPEG image and convert that to pixel values. And sometimes they will have no idea how to do it. So the first refactoring we did was to bring in the image processor from Hugging Face to skip that kind of image to pixel values processing, as well as abstract all the user interface to infer those metadata from the Hugging Face repo or store it somewhere in the vLLM repo. So as you can see here, we simplify the user interface a lot to initialize the model, same way as how you initialize like a typical LLM, just give me the Hugging Face model ID. And the prompt, there's no additional formatting needed. It's the same Hugging Face example prompt. And for the image, you just need to open that image with the Pillow image library. Pillow is a very standardized library in Python to kind of load image into their Pillow object. And finally, you just feed that to the prompt, to the LLM class, to the actual generation. This also unlocks us to do the end-to-end, like the OpenAI compatible inference that will give example later. But that's kind of the first milestone, simplify user interface, make it easy to use. And next, once we wrap up the work for Lava 1.5, we move on to Lava 1.6. So this is where we realize we need to support dynamic size of the multimodal embeddings. Recall in Lava 1.5, the image embedding size for one image is always going to be 576. This is a static number. We always it doesn't change depending on the input image. But for Lava 1.6, this changes. And this has been the case for a lot of models today, or the open source world, where your image embedding size actually varies depending on the input resolution. So sometimes your image embedding can be 2,000, and sometimes it can be 15,000. And you have to, the main task here is that depending on your input payload, you will have to pre-process the text sequence dynamically and to insert the right number of image placeholder tokens, because that's how we're gonna swap them with the image embeddings in the model execution time. In Hugging Face, you can see here as an example, they look at the input image, they get the right number of the image number of patches. These patches get converted to the actual length of the image embeddings, and they finally merge it with the text input tokens. But one problem is this happens in the model execution time, meaning the GPU doesn't know until you run this code. And this doesn't work on vLLM for two reasons. First reason is that on vLLM, our scheduler needs to know beforehand at a scheduling time how long that final sequence is, because that's how we allocate the resource, the KV cache, for the sequence, and how we decide if we're going to run the sequence or not or put in the queue. And secondly, this kind of like dynamic input shape changes at execution time is extremely prone to and also it doesn't work well with the torch compile kind of static shape input that we want to support in the long run. And you could argue that just move that logic out of the forward pass, make some helper function in the code base, make sure it works with the model. But then we quickly realized the challenges are, what if we want to generalize to multiple modalities? Like what if going forward, we're gonna have image, audio chunk, video frames, and each of them will have variable length. And what if each payload is like multiple items, right? What if I want to do multi-image inference, and each image itself is also variable length? And how do I properly profile the engine to reserve the GPU memory for the KV cache with all these multimodal data items? And what if there's some kind of additional pre-processing needed, or in this case, some model vendors can just define their own conversion from image to pixel values inside their own model repo, but not on Hugging Face or transformers. How do we do that? And finally, like, what if we want to do mixed modalities, right? Today, we don't have a model like that, but I won't be surprised going forward. We have a model that supports like image and audio and text inputs all together in the forward pass. So to kind of summarize the challenge here, the main goal here is to design a framework to process and format your input text sequence with the right number of multimodal placeholder tokens, as well as add a way so that the developers can add their own logic to pre-process these multimodal data items, meaning convert image to pixel values, convert an audio clip to a NP array, things like that. So this sounds trivial, but Cyrus and I actually spent a lot of time on designing such framework, and this is actually a very big design and engineering problem. I'll just skip through the whole challenge, I guess, like the journey, but I'll give you the solution. So at the end, we kind of lands on this registry-based solution, and you can skip the text on the left, because I will show you an example. So on the right, we have an example of the QN2 VL model just came out. Actually, they made a model PR from the QN team. And here, you can see that this model takes image and video as input. The way we register, kind of like accept the modality, is that we have a register mapper. This defines which modalities are accepted to this model, and how do you want to process the input data to the actual kind of last mile processing here. And you can see here they actually write their own like input mapper for this model. And secondly, this multimodal registry is also responsible for defining the max number of image tokens for each modality. A good analogy here is that a max number tokens for each modality is like how you specify the content length of your input text. Because you do want to send like a limit. If it's beyond the limit, then we cannot reject or we cannot accept that additional modality. And for the input registry, what we do here is that in order to profile the engine to allocate the right number of like KV cache for the engine, we need to define how a dummy sequence looks like with their corresponding dummy input data items. And finally, we have an input processor. I know it sounds a bit vague, but this is where we put a logic to formulate, I guess, to format your Hugging Face compatible prompt to the actual sequence that the model will see. This means like extending the tokens by the actual number of like image embedding size tokens in the input prompt. So once we kind of like finish this refactoring, I'll just show you like the OpenAI Vision API compatible inference here. So today you can use vLLM to serve Pixel. Good shout out. I want to shout out to Mistral AI. They actually came directly to us to kind of open source this model. This model was not even on transformers before vLLM merged the PR. And as you can see here, you can serve the model without too much like metadata. The only metadata you specify here is that you want to limit the number of images to be 2. And once you start the server, you can use your OpenAI client to call the server. We are fully compatible with the Vision API, meaning you can send in either a image URL, a remote URL, or a data base 64 encoded image. And I want to shout out to Fix AI from Seattle. They are a startup. They developed this audio language model. Same way you start a server, and then to call the server, you specify audio URL. You can put in like an audio base 64 encoded kind of a string, or the actual remote location of the audio clip. Same, it's basically the same interface. Yeah. And I want to call out today that we support over 10 large multimodal models, and we support text input, image input, audio input, and video input. I also want to emphasize that vLLM actually the support came directly from the model vendors. As I mentioned, Pixel and Llama 3.2, we got day one release of these models, and we are very happy to work with model vendors going forward to open source their models or release their models on vLLM on day one so that users can try them out immediately. Actually, I know a lot of researchers, they use vLLM for fast iteration evaluation when the model comes out, and vLLM has been their default choice to batch process these evaluation suite very quickly. Okay, we don't talk about, it's a vLLM talk, so we always gonna talk about performance optimizations. So we enable large multimodal models on vLLM, and next I'll talk about how we optimize these models. To recall, these models are leveraging a decoder-only language model plus a multimodal encoder, meaning they are only different from the traditional LLMs at prefill stage. This is because you, in addition to tokenize your input text, you have to process adding the additional logic to process the input text prompt, and as well as converting your pillow images to pixel values, and finally run your features through this vision encoder and projector to get embeddings and merge them with your text embeddings. That's all done in the prefill stage. But at the decode stage, basically the generation stage, multimodal data is no longer needed because every information we have is already stored in the KV cache. So the inference pattern is identical to decoding. The first optimization we did was TP on the multimodal encoders. Just as a background, typically these encoders, clip encoder or Visp encoder, they are very small compared to the actual language model backbone. For instance, in Llama 1.57b, the clip encoder is only smaller than 500 million parameters. And previously, these encoders are replicated on each GPU if you deploy these models over multiple GPUs, because we feel like this small model, it doesn't really worth the engineering effort to tensor parallelize these encoders. But then later on, we see a huge kind of influx of small multimodal models. Polygamma 3B, 3.5 vision instruct, which is also 4.2B. And compared to these models, the vision encoder itself is actually relatively big. Meaning, if someone wants to serve these models over multiple GPUs, and each encoder is replicated on each GPU, you're in a 4 GPU kind of a scenario, you're basically wasting over a gig kind of a memory in the GPU. So we actually did the TP on all these encoders so that we can significantly save the space that can be reserved for the KV cache, which leads to higher throughput overall. The second kind of optimization we did was enable multimodal embeddings as the input. For the context, sometimes you don't have to actually run your multimodal data through that encoder. You can just run it somewhere else separately and generate these embeddings beforehand. And during inference time, you send the prompt and the embeddings directly to the vLLM engine. So the inference pattern is just identical to a typical LLM. And you can also cache or hash and cache them separately somewhere else outside of vLLM. So you have the developer will have a lot more freedom to control how they want to save these embeddings. But it does come with a trade-off. First of all, it adds additional complexity. Before, as a user, you just need to worry about sending prompt and your pillow image or JPEG image. But now you have to kind of pipeline that inference yourself. And also, sometimes the prefill for the image is actually not that much compared to the prefill for the text itself. So it's a debate whether it's really worth dealing with this kind of complexity to break up the inference pipeline. And before I kind of wrap up to go to the future roadmap, I added a bonus topic here, multimodal Llama 3.2. Actually, I added this slide last night because it came out last week. So first of all, I want to give a brief overview of what the multimodal Llama 3.2 looks like. It's actually very different. It's a totally different beast than the other kind of vision language models or audio language models out there because it involves cross-attentions. So unlike other models that concatenate your image embedding with your text embedding, there's actually like cross-attention layers in the language model itself. And the initial PR for this model was contributed by Chen, who's a visiting researcher at Skylab, with a partnership with Meta. And some challenge we face here is, I mentioned there's additional cross-attention layers only when the image is present. Meaning, if it's text input, then these are not visited. If there's an image, then we have to run through these cross-attention layers. This kind of dynamic inference pattern is a little bit tricky to deal with. And secondly, there's custom attention mask required between the text and the images. Traditionally, for attention module, we assume a causal kind of attention mask because that's how LLM works. But this kind of new mask is something we have never dealt with before. And finally, since this is a cross-attention layer, meaning there will be the encoder and decoder block tables. So we have to come up with a way to more efficiently manage the memory for these architecture, which Kuntai mentioned in the roadmap in the last talk. And there's a mini roadmap for this model in particular. Please see the issue AA26. And next, I'll talk about the roadmaps. So what are the to-dos? First of all, we want to make multimodality support to be compatible with all the features on vLLM. First one is automatic previous caching, which Johan talked about in the last talk. So if you think about previous caching, right now it's down on the token ID level. But for image input in particular, the token IDs are identical to all of them, no matter what image you're sending. Meaning we need to add additional hash on the image itself. Second is chunk prefill. We need to precisely track where these placeholders are in order to chunk prefill them properly. And we also need to make sure it is compatible with the latest optimization that we added to vLLM, multi-step scheduling. On a second track, we also have, as Rohan mentioned, CPU overhead is something we really want to get rid of in the whole inference pipeline. But we do have these processing to convert image to pixel values are indeed happening on CPU today. And we want to have better and more efficient implementation or pipelining to pre-process this multimodal data. And there's a few more items, better profiling strategy, quantized LLMs, and LLMs with LoRa's. And I want to wrap up with some unknowns that I personally now, I don't even have an answer yet, but it's just for the interest of the audience. So I think in the overall large multimodal model world, we still haven't figured out the ultimate architecture of LLMs. It is Lava based. You merge the embeddings together and send to a decoder only language model. Is it Flamingo based, so multimodal Llama, where you add cross attention between text and multimodal data? Is it chameleon style, where you actually tokenize all modalities into token IDs and you leverage the language backbone? Or is it transfusion? It's a very interesting paper that came out of Meta AI, I think a month ago, where you merge a autoregressive transformer with diffusion in the same model, and you switch mode during the inference. And we don't know what's coming out next, right? And the other unknown is how do we think about multimodal output? Right now, we are only limiting our scope to multimodal inputs, to text output, but does it make sense for vLLM to support multimodal output? Until which point we see there's really a strong need for us to support multimodal output, and does it make sense? And I think that's it for everything. So thank you for listening. Please check out the workstream tracker, issue 494, and contact me for any questions, and we welcome any feedback and contributions to this workstream.
All right. Please raise your hand if you have questions for Roger, and I'll run the mic. Any fun questions about multimodality? There's a question back there.
Okay, first of all, thanks for the presentation and all your contribution in vLLM. Very useful for the future, definitely. I wanted to ask you about how your approach to supporting multimodality compares to other inference engines, like TGI for Hugging Face, for instance.
So I actually, like when I designed kind of the framework for support for multimodalities on vLLM, there was nothing, right? Because vLLM itself was designed to work with language model itself, decoder-only language model itself. So when I checked, I did check TGI for inspiration, and I think the way that they did was, as I mentioned, adding some hacks. So for Lava Next, they put in some helper functions in the same model file. It's not really like a core part of TGI. It seems like a sidetrack support or second class support for the inference engine, and that's why Cyrus and I spent a lot of time designing the overall infrastructure to make sure developers can come in very easily and pull their models versus it's like a second class treatment in the inference engine.
So when you develop this this new framework, how do you? What's your workflow for optimizations? Do you start with profiling tools and collect the statistics, and then writing a try-10 kernel? Then, if not work, then go to CUDA kernel.
Yeah, this is a great question. I think for Trident or CUDA kernel in particular, we didn't get to that. The first step we did was to, as I mentioned, for the TP of the vision encoder, these are very small. So sometimes actually not worth, it actually won't improve performance if you shard it over a lot of GPUs, because these are very small. So the communication overhead actually overshadows the benefit you get from TP. When we test out different kind of models to see the effect of TP on these vision encoders, we actually don't see that much speed benefit. There's actually no speed benefit at all. But we did see that you save a lot of GPUs. I guess you save a lot of memories on GPU, and these memories can be kind of freed up for the KV cache, meaning you can send in a higher batch of requests compared to before, and this will overall lead to a higher throughput. But for performance itself, TPing these applying TP to these encoders actually don't bring the benefit of speed. Yeah.
Is that because the activation is actually very large? So have you tried sequence parallel?
Can you repeat that again?
Have you tried sequence parallel instead of tensor parallel? I guess multimodality has a very large application.
Not quite, because again, most of the compute happens in the language model backbone itself, and the activation for the vision encoder is only one time at prefill stage, and these are very small. Yeah, because the clip encoder is actually only 400 million parameters. These are very small compared to the language model backbone itself.
Okay, so you mean the activation cluster between each layer is actually much smaller compared to
For the vision encoder, yes. That's actually very small compared to the actual language backbone. Yeah.
Cool. Maybe we'll have time to take one more question. If not, I'll ask a question.
Yeah.
What's your favorite application of multimodal models?
Say that again?
What's your favorite application? How are people using these models? Nowadays?
Can I say it? I think a favorite application I have is imagine coming to a 3D world, right? You want to understand what's going on in the 3D world. One way to do it is, especially for multi-image, is that you can take different screenshots of this 3D world and send it to the language model to have it describe it without you actually play through this 3D world. Right now, we can only limit that to kind of an image-based inference, but we don't know what's going on. We don't know what's going to be happening in the future, right? Maybe there will be a 3D encoder coming out in the future that you can kind of put it together with the language model and have the language model do the reasoning to describe this 3D world. Yeah.
Awesome. Thank you so much. Let's thank the speaker.